Hey everybody, in this video I'm going to teach you everything you need to know to start working with pandas. So I encourage you to sit back, relax, and enjoy the show. Pandas is a Python library built on top of NumPy. It's widely used in data analysis, data science, and machine learning. The name pandas comes from the term panel data. Unfortunately, it has nothing to do with pandas, the animal. Using this library, you typically work with objects known as series and data frames. A series is like a one-dimensional labeled column. A data frame is like a two-dimensional labeled grid or table. With this library, you can import, display, manipulate, and export tabular data. Think of pandas as Python's version of Microsoft Excel, but on steroids. Before getting started with the series, I would recommend learning everything up to Python lists. I do have a free 1-hour course on YouTube to catch you up to speed if you're interested. Here's how we can start working with pandas. Within your IDE, at the top, we're going to import the library of pandas, then give it an alias as PD, meaning pandas. You'll likely need to download this package, and honestly, the easiest way to do that, if pandas is underlined red, you can just simply install this package. That should clear up that warning. Otherwise, what you could do is go to your left toolbar and open up a terminal. You can also use the shortcut of Alt plus F12. You can use pip to install pandas. If you have multiple versions of Python downloaded, you'll need to use a different command if that doesn't work. Python-m, then pip install pandas. One of those should work for you. Then hit enter. To check the current version of pandas, we can print access pandas as PD, double underscore, also known as dunder, version, double underscore again. And the current version of pandas that I'm running is 2.3.2. All right, and we are ready for our first lesson. All right, everybody, to kick off this pandas series, I gotta talk about, well, series. A series is a pandas one-dimensional labeled array. Think of it like a single column in a spreadsheet. It's one-dimensional. A good analogy would be a single hallway with apartments. Each apartment holds some data. Each apartment also has some sort of label or number. A series is a one-dimensional labeled array. Here's how we can create one. We'll start with the Python list. Let's say we have some data. Then we'll add a few numbers. 100, 102, 104. I can convert this list to be a series. Here's how. I will create a series object equals access pandas as PD, call the series constructor. Now this is a constructor, not a function. The S is uppercase. As an argument, we will pass in our data. And then if I were to print my series object, here's what it would say. There's a couple things going on here. All of our data is arranged in a single column, 100, 102, 104. The left-hand side has an index. The index has labels starting with 0, 0, 1, 2. And on the bottom, we have metadata about this series. The data type of what we're storing are 64-bit integers, 100, 102, 104. If we were to change the data type, the metadata is going to change too. I'll add some decimal portions, 0.1, 0.2, 0.3, and let's see what changes. Now the data type is 64-bit floating point numbers, or we could use letters or strings. A, B, C. Now the data type of what we're storing are objects, or even booleans. True, false, true. The data type of this series is bool, meaning boolean, true or false. But let's change these back to be numbers. 100, 102, 104. Now when you construct a series object, you can set an index with custom labels. The default behavior for each label is to start at 0 and increment by 1, but we can pass in something custom. This will be another argument within our series constructor. We'll pass in a keyword argument for readability. Index equals. We can pass in a list, a tuple, a dictionary, a NumPy array, or even another series. To keep it simple, let's set the first label to be A, then B, then C. Here we go. Here are the new labels. With our index, we have new labels, A, B, C. But the values are still the same, 100, 102, 104. You could get creative with your labels. For example, going back to our apartment analogy, let's say apartment number 1, then apartment number 2, then apartment number 3. We have apartment 1 is 100, apartment number 2 is 102, apartment number 3 is 104. We'll change that back. If at any time you need to access a value directly within a series, you'll take your series, access the lock property. Lock means location by label, but people just say lock. Use the subscript operator, which is a set of straight brackets. Then you will select a label. For example, A. Return the value where the label is A. This will return a value, whatever is at this label. A is 100, B is 102, C is 104. If there's a label that doesn't exist, like D, we get a key error. Let's change that back. To update one of these values, we'll have to access that lock property. Take our series, access the lock property within the subscript operator, locate the value at label C. Then let's set this to be 200. Then we will print our series. C is now 200. So to print or access a value, you access the lock property. We're locating a value by label. Now you can also locate by integer position. That's iLock. Series dot the letter I, lock. If I need the first value, the integer location is going to be 0. That returns 100, 1 is 102, and 2 is 104. It's pretty similar to accessing an array in other programming languages. So you got iLock for integer location, or lock, location by label. Okay, now we're going to filter by value. We'll need a few more values. Let's say we have 200 and 202. We'll need a few more labels though. Currently there's a mismatch. Value error, length of values 5 does not match the length of index 3. We'll add a few more. We have A, B, C, D, E. There we go. Let's filter by values. We will return any values that are 200 or greater. Here's how. Take our series, use the subscript operator, and here we'll write a condition. Return any values within our series that are greater than or equal to 200. This will print the label of D has a value of 200. The label of E has a value of 202. Let's switch this to be less than 200. A is 100, B is 102, C is 104. Alright, here's a more complex example. Rather than using a Python list for this next example, we'll be using a dictionary. As you guys might know, I really like pizza. And well, I need to go on a diet because I've eaten too much pizza. I'm going to use a Python dictionary to record how many calories I've eaten per day. I'll create a dictionary, we'll name it calories. Calories equals a Python dictionary. A dictionary is made of key value pairs. For the key of day 1, for the value within this key value pair, I'll set this to be 1,750, meaning 1,750 calories. I'm trying to eat less than 2,000 calories per day. If you would like, feel free to pick different numbers. For day 2, I didn't stick to my diet on day 2. I had 2,100 calories. Then for day 3, I had 1,700 calories. Now to create a series again, we will type series equals access pandas as PD, call the series constructor, then pass in our dictionary. Since our dictionary is made of key value pairs, we'll use the keys as the labels. So you don't need to pass in an index, like this. If we were to print our series, here's the output. This single column represents the calories I've eaten each day. And on the left-hand side is each label for this column. We have day 1, day 2, day 3. Let's access the log property to see how many calories I've eaten on a certain day. Day 1, 1,750. Day 2, 2,100. Day 3, 1,700. Now let's update day 3. Perhaps I cheated on my diet and I had a cookie. Well, to update a value, we'll access our series, access the lock property, we're locating by label. At the label of day 3, we'll add 500 calories. We'll say plus equals 500 to add 500. Now on day 3, the total amount of calories I've eaten is 2,200. If I were to print my series, here's what my chart looks like. 1,750, 2,100, 2,200. Let's delete this line of code. Now we'll filter by value. Let's find any days where I've eaten more than 2,000 calories. Which days have I not followed my diet plan? We'll access our series, use the subscript operator, return any values within our series that's greater than 2,000. We'll say greater than or equal to 2,000. Alright, on day 2, I did not stick to my diet. I had 2,100 calories. Now on which days did I stick to my diet? Return any values within my series that are under 2,000. There are 2 days which I followed my diet, where the calories is under 2,000. Day 1 and day 3. Alright everybody, that's a series. It's a pandas one-dimensional labeled array. Think of it like a single column in a spreadsheet. Now your homework is to post a series in the comment section down below. If you can, try and think of a unique example. Alright everybody, and those are series using pandas. Alright, let's do this everybody. We gotta talk about data frames. In pandas, a data frame is a tabular data structure with rows and columns. It's two-dimensional, similar to an Excel spreadsheet. Here's a beginner-friendly way in which we can create a data frame. Let's start with a dictionary. We'll say data equals a dictionary. For our data, we'll have some employees. For the key of name, this will be a column. Instead of just having a single value, we'll use a list, a Python list. Here we can list a few different names. I'm going to use SpongeBob characters because most people know who SpongeBob is. We'll have SpongeBob, Patrick, and Squidward. Then we'll add another column. This column will be for the age. How old is each employee? The value will be another Python list. I'm going to say that SpongeBob is around 30. Patrick will be 35. Squidward will be 50. Let me just do a little bit of organizing. There, that looks pretty good. Now, we're going to convert our dictionary into a data frame. Here's how. We will assign data frame, but most people shorten this to just DF, meaning data frame. Our data frame object equals access pandas as PD, call the data frame constructor. Now the D is capital, not lowercase. That's because this is a constructor rather than a function. We're going to pass in our data, our dictionary. And then we will print our data frame, which we have named df for short. And here's our data frame. It's tabular data. It's made of rows and columns. We're also given an index. This index has a label for each row, starting with 0. But you can set that to be something custom. To do so, when we construct a DataFrame object, we will set an index by passing in a keyword argument. Index equals a Python list. We'll say employee1, then employee2, then employee3. And we should have some new labels. There we go. Employee1 is SpongeBob, age 30. Employee2 is Patrick, age 35. Employee3 is Squidward, age 50. If you need to select a single row, you can access the lock property. df.lock, subscript operator. Lock means location by label. Give me all the data for employee1. That's the label. We are given SpongeBob, age 30. Here's the label, and the data type of this row. It's an object. Let's select employee2. Patrick, age 35. The label is employee2. The data type for this row is an object. And employee3. We have Squidward, age 50. Employee3, data type is an object. Now you can also select by integer location by using the iLock property. iLock. So the index 0 will give you the first row, which is again SpongeBob. 1 is for Patrick. 2 is for Squidward. Let's just print the entire data frame. Now, if you need to add a new column, here's how. I'll just add a comment. Add a new column. And I'm just going to zoom out a little bit. To create a new column, we'll access our data frame, use the subscript operator, then we'll need to think of a new column name. Let's say job or position. What does everybody do? We will assign this to be a Python list. The number of values must match the number of rows. We have 3 rows, one for SpongeBob, Patrick, and Squidward. In that order, what is the job of SpongeBob? He is a cook. That's the first value. Let's say Patrick is a new employee. He doesn't have a position quite yet. For the time being, we'll say NA for not available. And then Squidward is a cashier. Now let's print our data frame, and we should have a new column. Employee 1 is a cook. Employee 2, their job is not available yet. And employee 3 is a cashier. That's how to make a new column. Now, how do we add a new row? Here's how. Add a new row. An easy way to create a new row is to create a new data frame, then concatenate it. We'll say new underscore row equals access pandas SPD, call the data frame constructor again. Now we're going to pass in a list. For this list, you can add a dictionary for each new row you want to add. For example, if I need to add 3 rows, I'll need 3 dictionaries within this list. But for now, we'll just add 1. This dictionary needs key value pairs. For the key of name, we'll add, let's say, Sandy. For the key of age, we'll add a value of 28. Then for the key of job, we'll add a value of, I would say that Sandy's some sort of scientist or engineer, but we'll just say engineer. This is a separate data frame. It only contains a single row, a new record for Sandy. We're going to concatenate it to our existing data frame. We will reassign our data frame, df equals access pandas SPD, call the concat function for concatenate. You may see people use append, but that's now depreciated. We'll be using concat for concatenation. We will pass in a Python list, then include all of the data frames we want to concatenate. we want to include our existing data frame and the new row. And then let's print our data frame, and we should have a new row. Yes, we have a new row for Sandy. However, we have not set an index. The index was set to 0. Well, we can manually update that. When we create a new data frame, you can pass in an index as a keyword argument. We'll do that for Sandy. So, comma, space, and just for readability, I'll put this on a new line. Index equals a Python list with a new label for her of employee 4. And here we go. Employee 4 is Sandy, age 28. Her job is an engineer. Now you can add more than one row. Let's add new rows. This variable will be new rows. So within our list, we can add more than one dictionary. Let's add another row. I'll do some copying and pasting just to save a little bit of time. Copy all the key value pairs and paste it within the new dictionary. Let's say the new employee is Mr. Krabs. His first name is Eugene Krabs. He seems like he's about 60. His job is that he is a manager. We'll assign him to be employee 5. And then we are adding new rows to our data frame. All right, let's take a look. There they are. We have 2 new rows. One for Sandy and another for Eugene. Sandy is 28. She's an engineer. Eugene is 60. He's a manager. All right, everybody, those are data frames. Data frames are a tabular data structure. They contain rows and columns. Your homework is in the comment section to post the output of a data frame. Try and think of a unique example if you can. And well, everybody, those are data frames using pandas. Okay, let's do this, everybody. So in this video, I'm going to show you how we can import CSV and JSON files using pandas. You will need some data to work with. For this demonstration, on my desktop, I have 2 files. One is a CSV file, meaning comma-separated values, and the other is a JSON file, .json. For this demonstration, you'll need some data to work with. I looked online and I did find a CSV file that contains the stats for the original 150 Pokemon. For this video series, I'll be using Pokemon because many of us have grown up with Pokemon. We can relate to it. But feel free to use any kind of data that you would like to work with. Just make sure that it's in a CSV format. So for my data, for number 1, we have Bulbasaur, all the way to number 150, where we have Mewtwo. But again, the data you want to use is up to you. If you would like a copy of this data, I'll post it in the comments section on YouTube. You can just copy and paste it, like so. Then to create a CSV file, wherever you would like to place this file, right-click, go to New, Text Document, open it, paste your CSV data, save it, then be sure you save it as a CSV file, for example, data.csv. Then once you have your CSV file, for convenience, I'll move it to my Python project folder. My CSV file is right next to my main Python file. We're going to create a data frame using our CSV data. df meaning data frame equals access pandas as PD, call the read underscore CSV function, and then we have to pass in either a relative or absolute file path. This file is right next to my main Python file. I just need the file name, including the extension. In this case, it's data.csv. Let's take a look at our data frame. I will print my data frame. And here's what we have. I have 150 rows and 7 columns. The data we're outputting, it's truncated. If you print the data frame directly, you'll be given the first 5 rows and the last 5 rows. Here I have the Pokemon from Bulbasaur to Charmeleon, numbers 1 through 5, and the last 5, Moltres to Mewtwo, numbers 146 and 150. If you need to print all the data in your data frame, to print the entire data frame, all the rows and columns, and not a truncated version, following our data frame, we will call the toString function. Be careful when working with a very large file, you'll print everything. This file isn't that big. We only have 150 rows. So now we display all the data for our Pokemon. A few of the columns include their number in the Pokedex, their name, their first type, such as grass, fire, water, their second type if they have one. Bulbasaur, Ivysaur, Venusaur are also a poison type, but many of them are missing a second type, such as Charmander. Charmander doesn't have a second type, so the value here is not a number, NaN. There's a height in meters, a weight in kilograms, and a legendary status, which is either 0 or 1. If this Pokemon is not legendary, they have a legendary value of 0. If they are legendary, for example, Mewtwo has a legendary status of 1, meaning that there's only ever one Mewtwo. That's what it means by legendary. Now, to read a JSON file, here's a JSON file that contains the same data. JSON means JavaScript Object Notation. For entry number 1, we have Bulbasaur, Ivysaur, Venusaur, all the way till Mewtwo, which has a number of 150. For convenience, I'll place this JSON file within my project folder. And then to read a JSON file, we will call the readJSON function. And then pass in the name of that file, including the extension, data.json. And here's what we have. We have our same data again. All the original 150 Pokemon. Alright, that's how we can read a file using Pandas. I couldn't think of any homework for you to do, so to increase engagement with this video, post the name of your favorite Pokemon down in the comments section. Alright everybody, and that is how to read both CSV and JSON files using Pandas. Why, hello again everybody. In this video I'm going to show you different selection techniques using Pandas. In the previous lesson, we've loaded a CSV file. Here's what my data frame looks like. My data frame contains the original 150 Pokemon, all the way from Bulbasaur to Mewtwo. Alright, so we have a data frame. To make a selection by column, I'll just add this as a comment, selection by column. What we'll do is print access our data frame, use the subscript operator, then we will pass in a column name. We are going to pass in the name column. And here's what we have. As a single column, we have all the names, and this is actually a series. If you have a lot of data to print, the default behavior for Pandas is to print the first 5 rows and the last 5 rows. What you see here is a truncated version. If you need to print the entire thing, follow this with the toString function. Do be careful if you have a lot of data you're working with. And here are the names of the original 150 Pokemon. Let's say we need the height column. Well, I'm going to do a search for height. I will place that within the subscript operator. And here's the height of every Pokemon in meters. Or the weight. We are searching for the column of weight. And here are all the weights. This one's heavy, whatever it is. I think that's Venusaur. 100 kilograms. Now to select multiple columns, we are going to print, access our data frame, then within the subscript operator, we'll pass in a Python list. A list of all the columns we would like to output. Let's output the name column, the height column, and the weight. We have 3 columns, the name, the height, and the weight. Then to display all the data, all the rows, you can follow this with the toString function. toString. And we get all the rows, and these 3 specific columns, name, height, weight. Alright, that is selection by column. Now we'll make a selection by row or rows. Let's take a look at our data frame. I'm going to print my data frame. Each of these rows has a label. The default behavior for pandas is to give each row a number for the label, starting with 0. They're in ascending order. Well, we can access the lock property, then pass in a label. So since I didn't set a label for each of these rows, 0 would correspond with the first row, where we have Bulbasaur. 1 would be Ivysaur. But optionally, what you could do, I can set one of the columns to serve as the index, so that you can access one of the names by label using the lock property. You're probably not going to remember which Pokemon is 145, but you'll remember it by its name, so it's easier to look up. So what you could do is that when we read our CSV file, we can pass in a second argument, a keyword argument, index underscore col, meaning column, index column equals name. Then let's take a look at our data frame. Now we're setting the label of each row to be the Pokemon's name. We can do a search by name pretty easily. So to set that up, you just pass in a keyword argument of index column, index call for short, then set which column you would like to serve as the index. So then when we access our data frame, we will access the lock property, meaning location by label. Then let's do a search for Pikachu. We'll pass in a string of Pikachu. And here's all the data for Pikachu. Pikachu is number 25. Type 1 is electric. Pikachu doesn't have a second type. That's NaN, not a number. The height of Pikachu is 0.4 meters. Weight, 6 kilograms. Pikachu is not a legendary Pokemon. Here you have the name and the data type of what Pikachu is. It's an object. All right, let's do a search for Charizard. And here's Charizard. Charizard is number 6, type 1 is fire, type 2 is flying, height 1.7 meters, weight 90.5 kilograms, not legendary. If you don't want all the data when displaying your row, when locating by label, we could pass in a second argument. We could pass in a Python list of all the columns we would like to select. So with Charizard, I would just like the height and the weight. So we will pass in a Python list as the second argument that contains the columns we would like to display. There we go. With Charizard, we only have the height and the weight, those two columns. Now you also can select a range of rows as well. After the Pokemon's name, you're going to use the slice operator, which is a colon. Give me everything between Charizard and, let's say, Blastoise. There we go. We have Charizard, Squirtle, Wartortle, Blastoise. You can also use integer-based indexing if you so choose. We're going to print, access our data frame, access by integer location. Let's say you need the first 10. You would pass in those indices. 0, 11. Remember that the second number is exclusive. You would then be given the first 10 rows between Bulbasaur and Metapod. Maybe you need every second row, then add a step of 2. Now we're given every second row. You can see that the number is going up by 2. As a second argument, you can select the indices of which columns you would like. I would like the first 3 columns, 0, 3. With the range of 10 indices that I've selected, I specified I would only like the first 3 columns. Besides our index with all of our unique labels, we have the first 3 columns, each Pokemon's number in the Pokedex, their first type, and their second type if they have one. Alright, now we'll go over an exercise. We'll have a user type in the name of a Pokemon, and then do a search for it. We'll create a variable of Pokemon equals, call the input function to ask for some user input, enter a Pokemon name. Using this technique, if the Pokemon's name doesn't exist, it's going to cause a key error. Using a try block, we will try and print, access our data frame, access the location property. Then instead of placing a string here with the Pokemon's name, such as Pikachu, we'll place in the string variable of Pokemon. We'll do a search for whatever the user types in. Now, if that Pokemon doesn't exist, we will catch an exception if it happens. Except key error, where we will print, I'll use an F string, we'll say that Pokemon's name, Pokemon not found. And now we can do a search for a Pokemon. Let's test it. Enter a Pokemon name. I'll type in Pikachu. Make sure that the first letter is capital. And here's the stats for Pikachu. Let's do a search for Snorlax. And here's the stats for Snorlax. What if there's a Pokemon that doesn't exist, like whatever that is? Well, this Pokemon was not found. I couldn't think of any homework for you to do, so let me know what your favorite non-coding hobby is. Post it down in the comment section. And that is selection using pandas. Hey, what's going on everybody? I'm going to explain filtering using pandas. If I could summarize what filtering is, it's basically keeping the rows that match a condition when working with the data frame. In the previous lessons, we've been working with the data frame that contains the original 150 Pokemon. Make sure that you have some data to work with before starting this lesson. Let's say I would like to create a new data frame and filter any Pokemon that have a height above 2 meters. We would have to access this height column and return any rows where the height is 2 meters or above. Here's how we can do that. Let's create a new data frame. We'll call it tall Pokemon equals, we will access our data frame, use the subscript operator. Let me zoom in a little bit. We're going to return a series. Access our data frame, use the subscript operator. We will select the column of height. Then we will write a condition. Return any rows where the height is greater than or equal to 2. And then we will output our new data frame, tall Pokemon. And here's what we have. We have filtered out any Pokemon that have less than 2 meters for height. You can see that with the height column, all the heights are 2 meters or above. So really with filtering, we're just keeping the rows that match a condition. Let's apply another filter. Let's say heavy Pokemon. Heavy Pokemon equals, access our data frame, use the subscript operator. We will select the column of weight. Access our data frame, subscript operator. We will select the column of weight. Return any Pokemon that have a weight that's greater than, let's say greater than 100. And then we will print our heavy Pokemon, that new data frame. And here we go. We've returned all the rows where the weight is over 100. Now let's return any Pokemon that are legendary. If a Pokemon's not legendary, this value is 0. If it is legendary, it's 1. We'll create a new data frame of legendary Pokemon equals, access our data frame, use the subscript operator. We will select the column of legendary. Now I set this equal to be 1 if it is legendary. We have 4 legendary Pokemon: Articuno, Zapdos, Moltres, Mewtwo. Now what you could do for readability, the Boolean value of true also equals 1. That would work too. If your CSV data contains Booleans, mine doesn't, you don't necessarily need double equals true. That's redundant. Since my original CSV data contains 0s and 1s, I would need that double equals. Let's find any water Pokemon. Water Pokemon equals access our data frame subscript operator. We will select the column of type 1. If type 1 is equal a string of water, then we will return any water Pokemon. Now this is only for type 1. We have Squirtle all the way down to Vaporeon. But what if their second type is water and not their first type? Well, we could use the OR logical operator. If you're going to use a logical operator, be sure to enclose your first condition within a set of parentheses. With the OR logical operator, this is a C-style operator. With Python, it would be OR. But we're going to be using the C-style operator, which is a vertical bar for OR. We'll write another condition, access our data frame, select the column of type 2, where the second type is equal to water. If the first type is water, or the second type is water, return that row. See, we have more rows. There's a few Pokemon that have a first type that's not water, but their second type is water. Now we'll use the AND logical operator. Let's find any Pokemon that are fire and flying. We'll name this new data frame just FF for short, fire flying. Fire flying Pokemon equals access our data frame. We'll do a search for any fire Pokemon. Select the column of type 1. Check to see if that's equal to a string of fire. Let's see what we have currently. Here's all the fire Pokemon, starting with Charmander all the way to Moltres. Now we'll see if their second type is flying. We'll be using a C-style AND logical operator, which is an ampersand. Be sure you're not using the Python AND. If we're using a logical operator, enclose your conditions within a set of parentheses. Now for my second condition, access our data frame subscript operator, select the column of type 2. Let's check to see if type 2 is equal to flying. Now we're returning any fire and flying Pokemon. And there's two, Charizard and Moltres. Their type 1 is fire, their type 2 is flying. Alright everybody, that is filtering. Basically, you're keeping the rows that match a condition. For your homework, to help increase engagement with this video, in the comments section, post a data frame where you search for 2 different types. Try and pick some different types that we haven't used yet. And well everybody, that is filtering using pandas. In this video, I'm going to explain aggregate functions using pandas. Aggregate functions, they reduce a set of values into a single summary value. Basically, we're reducing a bunch of values into one. We use aggregate functions to summarize and analyze data. In this demonstration, I have a data frame that contains the original 150 Pokemon. Let's say for some of these columns, such as the number, the height, the weight, and legendary status, I would like to find the mean, or the average. To find the mean for all numeric columns, we could do the following. When we output our data frame, we will call the mean aggregate function. But there's one thing we're missing. We can't use the mean function on any columns that are non-numeric. We can't find the mean for anything that's non-numeric, such as Pokemon names. They're alphabetical characters. What we could do is that when we call the mean function, we can pass in a keyword argument. Numeric underscore only equals true. We're telling pandas, find the mean of any columns that are numeric. And here's what we have. The average number is 75.5. The average height is 1.2 meters. The average weight is 46.2 kilograms. The average amount of legendaries is 0.02, 2%. So we have mean. Let's do some copying and pasting. Another aggregate function is sum. Let's sum all the numeric columns. And here's the sum of all the numbers, the sum of all the heights, the sum of all the weights, and the sum of the numbers of all the legendaries. Let's find the minimum. We will use the min aggregate function. The minimum number is 1, the minimum height is 0.2 meters, the minimum weight is 0.1 kilograms, and the minimum legendary status is 0. Then we have max. We will call the max aggregate function. Here are the max values: 150, 8.8, 460, 1. We also have count. With the count function, we don't need to pass in a keyword argument. We are counting the number of values within each column: 150, 150, 150. Now, not every Pokemon has a type 2. That's why this is only 67. Count won't include any null values. That's why this number is 67, and the rest is 150. That's using aggregate functions with an entire data frame. These aggregate functions would apply to the whole data frame. The next set of aggregate functions will be for a single column. All right, just to save a little bit of time, let's do some copying and pasting. We'll copy our 5 previous print statements and paste them. Now, rather than selecting the entire data frame, we will select a single column by using the subscript operator. Then selecting a column, let's pick height. What is the average height? Since height is a numeric column, we don't have to pass in this keyword argument. What is the mean of the height column? That is 1.2 meters. Then let's do this with sum. Subscript operator, select the column of height, and we don't need to pass in that keyword argument. What is the sum of all the heights? 180 meters. Then let's do this with min. What is the minimum value? What is the minimum height in this column? That is 0.2 meters. Subscript operator, we will select the column of height, and we don't need to pass in this keyword argument. With our column of height, the maximum value is 8.8 meters. And what's the count? Select our column of height, and the count is 150. That's 150 non-null values. But if I was to pick a different column, like type 2, well, if we remember, that was only 67. All right, that's how to use aggregate functions with a single column. Select your data frame, then select the column using the subscript operator. Now, there's also something called group by. Group by is a function. Now, if I was to print my data frame, I will print my data frame. We can arrange our data frame into different groups. We can group together rows by something that they have in common. Let's group our data frame by each creature's type, their type 1. We'll put all the grass types in one group, all the fire types in another group, and we'll do this with all the different types. We will do this by creating a group by object. Group equals access our data frame, call the group by function. Then we're going to pass in the name of a column by which we want to group these records by. We'll group by type 1. Now, if you were to output your group directly, here's what you would see. Group is an object. When you apply an aggregate function, the group object will return a series for you to work with and display. Let's take our group, select the height column, then call an aggregate function. What is the average height for each group? And we are grouping by type 1. Here's what we have. Here are the average heights. For bug types, the average height is 0.9 meters. Dragon types have an average height of 2.6. So we are grouping by each Pokemon's type, their type 1. Let's find the sum. We are grouping by type 1. Let's find the sum. All of the bug types have a combined height of 10.8 meters. All the dragon types have a combined height of 8 meters. Seems like water types have the greatest combined height. Let's find the minimum value from each type. We will call the min function. And here's the minimum values for each type, or the max. Here are all the max values for each type. And the count. Here's the total number of bug types, 12, dragon types, 3, electric types, 9, so on and so forth. There's a lot of water types I noticed. Alright everybody, so those are aggregate functions. They reduce a set of values into a single summary value. They're used to summarize and analyze data. And well everybody, those are aggregate functions using pandas. Guess what? It's me again. So today I'm going to explain data cleaning using pandas. Data cleaning is the process of fixing or removing incomplete, incorrect, or irrelevant data. Approximately 75% of the work that is done with pandas is specifically for data cleaning. You do a lot of it. In this demonstration, I have a data frame that contains the original 150 Pokemon. Now, let's say you would like to drop a column because it's not relevant. We're going to take our data frame, call the drop function. As a keyword argument, we're going to pass in columns equals, then within a Python list, you can list all the columns you would like to drop. I would like to drop that column of legendary. This function of drop does return a new data frame, so we're going to reassign our current data frame. Data frame equals, then call the drop function of the previous data frame. And let's take a look. We should be missing that column, which we are. Now let's say you don't want the number. Well, we can add that to the Python list. Drop, I think it was NO. Yes, that column is also gone. That's how to drop irrelevant columns. Here's how to handle missing data. In my data frame, there are many Pokemon that don't have a second type, but all Pokemon do have a first type. For example, Charmander. Charmander is a fire type, but Charmander doesn't have a second type. It's a pure fire type. If a row is missing a value within type 2, we're going to drop that entire row. Here's how to do that. We're going to reassign our data frame, access our data frame, call the drop NA method. We're going to pass in a keyword argument of subset equals a Python list. Any columns we place within this list will drop those rows if they're missing a value. Within type 2, drop any rows that are missing a value. When I display my data frame, I'm going to call the toString function just so we can see the whole thing. toString function. There should be no rows for Pokemon that are missing type 2. You can see that they're numbered here. 1, 2, 3, we go to 6 because 4 through 5 are missing. And then we jump up to 12 where we have Butterfree. We have removed any rows where there are null values within type 2. In place of dropping any rows where the values are not available, let's replace them instead with a different function. We will reassign our data frame equals, access our data frame, call the fill NA function. Fill any not available values. Within this function, we're going to pass in a dictionary. Within this dictionary, we'll select a column. We'll select type 2 again. Replace any not available values within the column of type 2 with the following value. Instead of not a number, NaN, we'll replace those values with none. And let's take a look. For type 2, for any Pokemon that don't have a second type, we've replaced any missing values, such as not a number, with the word none. That's how to replace any missing values. Number 3, we're going to fix any inconsistent values. We can replace any instance of a value with another one. Within type 1, let's select any grass types. we'll change any instance of grass to be all uppercase letters. Here's how you can do that. We're going to take our data frame, then select a column. Within the column of type 1, this will be a series that we're selecting. We're going to access that column using the subscript operator. We are selecting the column of type 1. Call the replace function, and then we will pass in a dictionary. Let's replace any instance of grass with the following value. This is a dictionary, we need a colon, then space. We'll replace grass with all capital grass to test it. And that should replace any instance of grass within type 1. There we are. Let's find a few more. There's more grass types: oddish, gloom, vileplume. This won't change any instance of grass for type 2, because we've only selected the type 1 column. Let's change a few more. Within our dictionary, we can pass in more than one key value pair. Let's replace any instance of fire with fire all caps. Let's do the same with water. Replace any instance of water within type 1 with water, all uppercase. Yeah, it looks good. Grass is all uppercase. Fire is all uppercase. Water is all uppercase. No other types are all uppercase. They're capitalized normally. Moving on. We can standardize text. Just to demonstrate, within our name column, let's take all the individual names and make them lowercase. Here's how you can do that. We will select the column of name. DataFrame, subscript operator, we are selecting the column of name. This is a series. Equals, select that column again. DataFrame, subscript operator, we are selecting name. That series. Access string, call the lower function. And that's going to take our column of name and make all of the characters lowercase. So that's how you can standardize some text. Number 5, I'm going to show you how we can fix or change data types. With my column of legendary, non-legendary Pokemon have a value of 0. Legendary Pokemon have a value of 1. I think Booleans would make more sense to use. We'll change these values to be Booleans. Here's how. We'll select a column, access our data frame, subscript operator, select the column of legendary. This is a series. We're going to reassign it. Access that column again, data frame, subscript operator, legendary, and I'm just going to copy this because I'm lazy. We'll call the as type function, and then pass in a new data type. For Booleans, you type bool. And now for the legendary status, it should all be Booleans. Dratini, Dragonair, Dragonite, they're not legendary Pokemon. That's false. But Mewtwo is a legendary Pokemon. That's true. Same thing applies to Articuno, Zapdos, Moltres. Here's how to remove duplicate values. Going to our CSV data, let's add a few extra copies of Pokemon. Let's add a few more copies of Bulbasaur. I don't know, a total of 4 is good. And then a couple for Mewtwo. We have duplicate entries. Let's print our data frame just to be sure that we do have the duplicates. Yeah, we got 4 entries for Bulbasaur. And then at the bottom, we have 3 entries for Mewtwo. To remove any duplicate values, we will reassign our data frame. Data frame equals access our data frame, call the drop duplicates function. Duplicates. And that's all you got to do. And now we should be missing those extra entries. Yeah, there's only 1 Bulbasaur. And there's only 1 Mewtwo. Alright everybody, so that is data cleaning. It's the process of fixing or removing incomplete, incorrect, or irrelevant data. On average, 75% of the work done in Pandas is data cleaning. It's an important topic. I couldn't really think of any homework for you to do, so to increase engagement with this video, I don't know, post your favorite anime in the comment section. And well everybody, that is data cleaning using Pandas.